Now the last thing that we're going to talk about in this little video presentation is the role that catalysts play in reaction rates. Now let's take a look at the potential energy profile once again of an exothermic reaction. This time we'll just draw it in. This is the reactants and this is the products. It's just arbitrary. It doesn't really matter what the reactants or products are. Now this reaction has an activation energy right here that's measurable. It's not very much, but it's noticeable. Now, what a catalyst does is actually, a catalyst is a substance that's added to a reaction. It's present in the reaction that lowers the activation energy, resulting in a faster reaction. And when it lowers that activation energy, essentially what it's doing is causing this reaction to go faster. Because it's easier to achieve activation energy. It's important to note that it doesn't actually take the same reaction and just make it go faster, but what it does is it offers an optional reaction pathway that is in fact easier to go. It's like the difference of walking around a mountain or walking through a mountain. If there's a tunnel, it's much easier to go through than it is to go around, speed-wise. If you're a train and you have an option to go around a mountain or take a tunnel through the mountain, it's easier to go through the mountain. That's what a catalyst is. It offers an alternate pathway for a reaction to go that is faster. Now in red, I'm going to draw in the catalyzed reaction, and you'll notice that the activation energy actually comes in, and I'm going to zoom in on this, and it's very poorly drawn, but I'll at least highlight it. There are two different little activation energies. It's almost like splitting the full activation energy into activation energy 1 and activation energy 2. But the point is that if you look, the threshold achieved to reach activation energy, or that activated complex peak, is lower in a catalyzed situation. The reaction goes faster because it takes less energy to reach the activation energy, or the required threshold. Now in a chemical reaction, catalysts are usually represented as being molecules over the reaction arrow. Take for example the decomposition of hydrogen peroxide. The catalysts, and there are many of them, but one of the catalysts that you can add to make this reaction go faster is to throw some iodine ions in, and so you list the catalyst over the top. Some other chemical reactions, as I was talking about with one of my classes last week, is platinum. And platinum is used in a lot of organic reactions because it forms a surface, and this is a platinum plate, and a reactant, and I'll just call it reactant R, can come in and form an activated complex with the platinum on the plate, and when it does that, it weakens the double bond in between, and then these two reactants can go off in their separate ways, no longer bonded to one another. So platinum, if I'm going to take R2 and I'm going to turn it into 2 moles of R, you might see platinum listed over the top of the reaction arrow, because that's something that happens specifically in catalytic converters in the mufflers of your car. They're loaded with pure platinum metal, which is a valuable metal, which is why they're sometimes stolen, cut out of the bottom of the cars and turned in for scrap for money. These are two examples of catalysts and how they make reactions happen faster. Let's just go back up to the picture above. Remember, just in summary, catalysts make the rate go faster because it offers an alternate pathway for a reaction to go, and it lowers the activation energy, and so the reaction can go from its reactants to products much quicker.
Before I finish, I want to talk about one more type of catalyst, which is known as an enzyme catalyst. Now, enzymes are biological molecules. These molecules are usually pretty gigantic, used in biological processes. Most of the time, at least in my experience in chemistry and biochemistry classes in my college days, was the enzyme was usually represented by a Pac-Man. And so it's usually drawn like this. The opening you see where the mouth is called the active site. Now the enzyme itself is a gigantic molecule with that active site, and what happens is the substrate, which is a biological reactant, inserts itself into the active site, And typically the way the substrate finds the active site is the substrate is coated with a bunch of polar molecules, and the enzyme is also coated with a bunch of polar molecules at the active site, and so the polar finds the other polar because polar and polar mix. Whereas the rest of the enzyme is nonpolar, so that's where it knows to fit into the enzyme itself. So anyway, the substrate goes in and performs the chemical reaction in the presence of the enzyme. And so it goes in and does what it needs to do, and then when the chemical reactions all finish, the substrate usually splits into two pieces, or whatever the chemical reactions, the goal of the chemical reaction was to accomplish two different products. Well, then the enzyme did its job. Now the substrate would eventually dissolve or split up into two eventually, but the enzyme's job is to speed up that process once again by offering an alternative pathway to get to the same result in the end. So the two biological products are produced and the reaction is over with the enzyme as the biological catalyst. Well, that takes care of this video lesson. Thanks for listening.